Okay, it's 3 o'clock. We'll get started. Today we'll be working on the chapter 2 basic tree theory. We have talked about the dynamic programming and also other things, but we will go visit the basic tree theory first, and then we'll go into the programming. Hi, Helen, how are you? Hi, Sherry, how are you?
I'm good.
Okay. And then, so we will talk about what is the tree structure and the basic tree structure theory, and also when you in the programming, how to use the tree. But today we just focus on the basic tree theory. So first we want to understand what is the tree data structure and how it can be used. Okay, and also how tree can be used to map data structure. And then use tree as a list. Use implement tree using list, or implement tree as a class, or use a tree as a recursive data structure, or use a priority queue that actually is some sort of array to implement heap. So these are different ways to implement a tree. Okay, but the purpose is that you want to finish some sort of computation. So you still need to have in mind that what kind of computation you want to compute. Then you choose the best data structure that you can use. So data structure and algorithm sometimes is actually matter a lot. Okay, it actually different data structure and different organization that can be different. Okay, so in computer science, the word graph refer to a set of nodes and vertices connected edges. So first you need to know about graph. Graph is a node plus edge. A node sometimes also called vertex. Okay, this is graph theory. An edge you have two kinds. One is directed edge, and another one is no direction edge. Okay, direction edge mean that you go from left to right, and undirectional edge means that you may go from left to right, may go from right to left. So, or like called bi-directional edge. Okay, so that actually is different. But graph for tree apparently is something that organized by some node and the edges. Okay. Hi, Sarah, how are you?
I'm good.
So basically, let me see. For Helen, what's the difference between a graph and a tree?
For a tree, there's only like one way to get from one node to another node, but for a graph, there can be many.
Can you have a tree that you actually go up and down here? Is that a tree?
No?
In fact, that's yes. So tree or not tree is not. So number one, tree is one kind of graph. Tree belong to graph. Tree is contained by graph. Every tree is one kind of graph. And then tree, you can have directional branches as well. So the only thing that you can say it's not a tree is when your graph is cyclic. Tree cannot be cyclic. Cyclic means that you have a circle among your tree, among your nodes. Okay? Is that okay? And usually we look at the top-down tree like this. But that's not a requirement that you can only go down. No, that may not be the requirement. You can also go up. Okay, that's also a tree structure. So basically, you cannot have circle, okay? And the total length from the top to the bottom, this is called 3 steps. And this node is called root. And the node that have no child, like we call this kind of node, leaf node. Okay, these are basic terminologies. So 3 are acyclic. All 3 are acyclic. Okay. So file system. Okay, here we talk about file system. So 3 usually is used for file system. So in real software implementation, usually in user code, I would say very few times you need to build a tree. Almost no. Almost every time you go to a recursive on one-dimensional array or two-dimensional array. Very rarely you need to build a file system using tree. But if you go to the Unix system, then file system is basically a tree structure. So basically, if you go to the Unix system, knowing what is inode. So inode is your Unix tree inode. Inode is your file structure. So basically, the kind of file you have is contained by inode and data block. And some extension can have more pointer in another inode, and then data block. So basically, this is a tree structured file system. Your tree really is used in operation system. Usually, only operation system is using tree. The algorithm problem is usually not using the tree structure. Okay, usually they want to have efficiency, so they want to have recursive call. They want to have the solution as quick as possible. They don't really care about the storage of the data. Okay, so your file system, you have E drive. Under there, you have many directory. So that's assume that we have Helen's directory. We have Eric's directory. So a lot of directory, and under Eric, you have many files. So that actually is an example of tree system on a hard disk. Okay. On the internet, same thing. You have your www.google.com. Under this page, you have many directory that you can access to. So it's another tree structure. Okay. And above the google.com, actually, you have www as a web domain. Okay. And it is one of the subdomain that Google has. And Google is under com. Okay, under the com group. Okay, so that's also another kind of a tree structure. So here we have data structure as tree. We also have, there are two kinds of tree. Last time we talked about it. There are two kinds of tree. There are basically one kind of tree that's actually called data tree. Data tree, if you organize your data in the tree format, okay, this is data tree. While the other one is called functional recursive call, calling tree. Calling tree is Fibonacci 5, calling Fibonacci 4, calling Fibonacci 1, 3, Fibonacci 3, calling Fibonacci 2 and 1. and then continue. So you may organize the data like this, you may organize the data like this, okay? And this is actually tree function code, okay, function code tree. This one is actually the data tree. And there is another kind called evaluation tree. Evaluation tree happen when, this is when you are playing tic-tac-toe. So first step is like this, and then you may have first step circle here. You may first step circle here. You may first step circle here. Okay, 3 possible locations. Some of them are symmetric. So totally there are 9 possible boxes you can put in, but some of them are symmetric. So there are totally 3 different styles. And then you can actually further go down to another level. So look at how the cross can play. Okay, there are many options. There are many options. So this kind of tree is called evaluation tree. So basically, a lot of game, Go game or a chess game, is going down to the evaluation tree to seek for the maximum win and minimum loss. So there is an algorithm called min-max algorithm. Okay, this is min-max algorithm mean minimum for the elements that damage and maximum for your step. So this min-max algorithm later we'll talk about it, but at this moment you just need to know that this data tree, this evaluation tree, there's also a recursive code tree. Okay, there is a standard min-max algorithm. Okay, this is a standard min-max algorithm that you can look at. Okay, so this is standard min-max algorithm. Usually, when you play game, the program need to be written down in this format. Okay. Okay, let's go back. Let's just talking about different kind of tree. So here we have actually the kind of tree for biology. Okay, biology had a kingdom, phylum, class, order, family, genus, species. Okay, and then this is for biology classification. And it can be a tree. It can be a tree. Tree is a family. And then under certain branch, you have some family. Okay, some family of the animal. So I think this belief that should be cats. Carnivores, well, carnivore is actually a meat-eating animal. Okay, and that's actually the different branches for the animal. Okay, that's actually classification also give you a tree. Okay, give you a tree. Inheritance structure is also a tree. Okay, file system is also a tree. And remember the document object model in Java HTML. It is also a tree. Okay, this is another tree example. DOM is also a tree. So basically, a tree can be, usually a tree is a pre-established data structure for your programming environment. Usually operation system or game engine or the web browser engine like to have some tree, okay? Because the tree can let them build up the data they have a good organization. Okay, so DOM also is a tree. So tree, we talk about node, edge, root, and path. Path is from your root to a certain leaf or a certain node. That's actually called path. How to get from the root to your node, that's called path. Children is the node below you. Parent is a node above you. Okay, sibling is someone you share a parent with you. Okay, subtree is the tree under you. Okay, lymph node we talk about it. Level is that from your root, how many steps can get to your point? That's actually how many level. And then to the deepest level, maximum level, we call it height. Okay. This one actually is the height. Okay. Definition one, a tree consists of a set of nodes and edges. So usually tree is written down as certain node that is vertex and edges. Okay. And binary tree means a node at most only have two child. That's called binary tree. That's called binary tree. And the tree may have multiple child. Okay, may have multiple child. This I think okay. Node and reference. So basically, usually we use node and the reference to build up your tree structure. Okay, so let's look at the tree structure to build an example. Usually, you need a class to build a tree or a structure to build a tree. First, let's use a structure to build a tree. Okay, let's look at a binary tree using the tree structure. Okay. Okay, we want to build a tree structure, so that's called structure. We declare structure. Let's call it node. This is C double plus. So this structure node actually is a type definition. So you have a integer data. And you have node body of the left. This is the pointer. and the node body of the right. Okay, and you also need to have a node constructor of no argument. In that case, data equals 0, left equals null, right equals null. So let's do this. Let's do data give it 0, left using null pointer, right using null pointer. Okay. So this is to use the structure to build a tree. And structure is actually more flexible. And you do not need to have an inheritance. Right here, we do not need the inheritance. So using the structure is okay. So let's have another constructor. Okay. So you have a constructor with no data, with a no parameter, and one data constructor. Let's have a 2 data constructor as well. 3 parameter constructor as well. Okay. So this is actually a tree structure. Now let's get started. Okay, so let's do node A1, B2, C3. Okay, so we create 3 nodes, and then okay. So right here you can have okay. Okay, let's see. Okay. So this can print out a string, but we do have the structure, okay? So we can also see out as age left. Okay, S left side to string is 2. A itself is 1, okay? Then now we print out the right side. Oh, there's no B's right side, actually, it's A's right side. Okay, so this give you the basic idea of what is a tree structure. And basically, this two-string program in the past, we actually use a string to convert it to become a the kind of the string that you can use for the CL format, but we actually have no time to copy it here. Okay, so just use the current version using the toString function to convert it to a string. Okay, but basically this one is a simple structure node for a tree structure. Okay, just give you the example of what is a tree structure. Anyway, if your data structure need to be tree, it will spend some time to build up the tree. So the tree usually is not used in competitive programming. It actually usually is used in the system programming, in the Unix, in the browser. They do want to have the tree data to be more better organized. Okay, and to save time, to save the access time. So usually data structure is used because of the efficiency of the programming, but in competition, usually seldom use the user tree. So you may have a binary tree, have a private key and 2 binary tree. So if you use a class, right here, you use the pointer to the class, okay? And you have a constructor, insert to the left, insert to the right. And the get right children and get right left children, and set root the value, suppose this root value, and then get the loop value. Okay, these are different things that for a tree structure can be built if you are doing class. Usually, I think that structure is better than class because it's easier to use. Okay, so it's that you create a tree with A and then insert left with B, insert right with C. And then set loop value to D. Okay, so these are the operation to help to do the binary tree. So there are many kind of tree. There's another kind of tree that used in the tokenization, used in the processing of the language. That's called parse tree. Parse tree means that your data coming in, you reorganize the tree, and you need to interpret the data structure and then try to convert it to a new language or convert it to a machine code. Okay, so that's called parse tree. So parse tree is actually using the tree structure to do syntax analysis, and then later use it to convert the input language to another language. Okay, that's called parse tree. So far we talk about parse tree. Data tree, functional code tree, and also the evaluation tree. Okay, different tree for different purpose. So here for this chapter, we more focus on the basic definition of the tree and understand what are the terminologies. And later we may go through each individual topic to explore more of the tree and then apply them to different problems. So this one is a parsing tree. Okay. So first you tokenize the whole article, making sure each word is that valid token. And then from the token, you decided that what kind of the token type you have. And then based on the token type, you find a grammar rule to reorganize to actually determine what kind of sentence structure it is, and use that sentence structure for later reasoning and later translation. Is that okay so far?
Yeah.
So basically, we can say that parsing tree is actually the root or the basics for AI, because you have a lot of language coming into your AI engine, and then you need to interpret it. You need to build them into different kind of the knowledge tree, and the knowledge tree following certain kind of grammar. So your AI is basically one kind of the parsing tree, and you based on your parsing tree to evaluate your data. That's why earlier we teach you how to evaluate the algebraic expression. That's actually a simple people evaluation tree. But later, when you evaluate AI tree, the tree can be much more complicated. But the idea basically is similar. The min-max tree we talked about a moment ago for the game design is also a evaluation tree. So parse tree is to pass the syntax, the input language into tree. But later, the same parse tree can also be used as the evaluation tree to evaluate the value. Okay. Any questions so far? As for how to do it, then there are a lot of things that you need to learn. Okay, there are a lot of things you need to learn. It's not just a talk. Okay, this different parse tree, different evaluation tree, the coding can be completely different. So the course of the data structure and the algorithm just teach you the basic idea of what is tree, what is graph, what is recursive. Basically, they teach you these three basic things. For more detailed computer science and also where this different data structure is used, you may need to study programming language, compiler, operation system, and algorithms. Okay. And AI, okay, different subjects in AI. So you will learn how these different data structures are being used. But in this course, as the data structure course, we primarily talking about the generic or basic idea of what is a tree and how they are operated and how they are organized. And later, how can you use it to do evaluation? Okay, these are basic idea of the data structure course. So this one is a parsing tree. You have times plus minus 7,352. So this one apparently is 7 plus 3 times 5 minus 1. Okay. And then if you use a postscript structure, it's actually is 7,3 plus 5 1 minus time. Okay. So the parsing tree, when you parse the things to be like this, you know it's algebraic expression. Then you may want to convert it to postfix and then actually evaluate when you need to do evaluation. Does that make sense? Does that make sense? So we write here the B3 is not a value, it's actually B. Then you don't evaluate 3, eventually B will get the value stored in B variable, and then the 3 is 4. Then you put 4 right there before you do evaluation. Okay. So aside of this parsing tree, there's another thing that living with it is called simple table. And when you start your parsing, your simple table already for the variable already been built. So you may have a B and that B actually built here, pointing to here. Okay, so you may have a simple table. And then when you actually found B, and then you directly will get the value and you will run it. So simple table and parsing tree are bound together in the compiler, and every time you need to parse the tree and evaluate the data, you will use them. Any questions so far?
No.
No. So the parse tree, I think we talked about it already. Okay, we don't repeat parse tree. Parse tree, you need to understand how to build fully parenthesized, okay, store expression in tree, and what kind of format you can evaluate. Okay. Okay, this one I think previously we talked about it already. So let's look at this one, 3 plus 4, 5, 4 times 5, okay? So you have 3 times 3 plus 4 times 5. So when you get the parsing and you get started here, you find out there is a value 3. And then there's a plus above it. And then you have a parenthesis. So inside parenthesis, you build a 4. And then star above it. And then actually with 5. And these 2 link with here. So gradually they do button up to build up your parsing tree. Okay. So basic parsing tree is being built from bottom up. Okay. So the textbook website do have this active call to build a parsing tree, okay? And this is the binary tree. And then there's a parsing tree, insert left, insert right, and then get left, get right, okay, those kind of things. And then when you build a parsing tree with your number expression, so this one is your equation of 1 plus 2 times 4, okay? If you get a string in, then you will build a binary tree based on the string that you give. Okay, that's the purpose. So right here, this program build a parsing tree of this one. And then after that, they do a post order search. So let's look at this program called build, parse build. Sorry, I cannot find the code, but let's do this. Let me see, this one is actually parsing tree. Let's copy it. Let me check, okay, let me check. There's also evaluation tree when you have. Let's see where they are, okay, one moment. Okay. Okay, I found it, okay. So I use this search to find, so it's actually under C double plus. Okay, let me copy it out first, okay. So let me do files, save as. So it's easier in Unlearn 1, chapter 1, okay. I'm sorry, it's in Unlearn 1, chapter 1. So let's actually open that. It's in here, Unlearn 1. No. Open folder in Unlearn 2. chapter 1. Okay, it's right here. So let's look at this BO, this one. BO pass tree, okay? And let's run it. Okay, so first you actually evaluate, you get 10, then you do post order to look at a tree. So you got you build a tree and then you do post order to visit the tree. So you have a 10, 5 plus 3 times. Okay, this is a post visiting. Okay. So this build tree will build that into a tree. Okay. Build a fully parenthesized program into a tree. So key point is here you actually have a constructor for binary tree, okay, providing the basic function for the constructors. And then BO trees is that you get a expression, and then based on that expression, you kind of put it into a tree structure. So basically, this portion, when you have expression to build, put into the tree structure is similar to the last time we do the conversion for postfix, infix to postfix, okay? Similar program structure. Okay, so let me just post this program for you. At this moment, I don't want to rewrite this one, but I want to give you the idea of what it is. So this one is the build parsing tree. The second program evaluation tree is just like last time. We do evaluation for the postfix structure. Same thing here. You convert it to the postfix first, and then you will evaluate the function for the. Okay. So PT means the postfix. Okay. And then that postfix string would be evaluated. The parsing tree would be evaluated by the evaluation function to provide a string, and that string got printed out. Okay. So basically this one has the reading of the evaluation tree and then get a value. So here apparently your evaluation tree is based on the data structure that you build by the BO tree, okay, by the BO tree function. Any questions so far?
No.
So let me also give you this evaluation tree function, okay? Okay, then so far we are up to here. Let's have a 10 minutes break. Okay, come back on 4 p.m. Okay, we'll continue. Today I'll try to finish this basic theory. Okay. Okay, we are back. Okay, so this one you build a tree and you do evaluation. So you add this program basically have a creator, operator class, and a to integer function, and then a to string to convert the data to a string. And then there's a evaluation tree pass tree that you build in the previous chapter. Build the left child with left child expression. Build the right child with right side expression. Okay. So your left child and right child both have the data, and you based on your evaluate function, you evaluate the expression. Okay, the expression. So this one is actually a recursive call. Okay, it will be a recursive call. So when you finish, there's a get value from the tree that would evaluate the data. Okay, this one is the evaluation of the tree. So to tree evaluation, you basically need to understand, for example, your tree node may be plus by 3. In this case, you will use the parent node to sum the two child nodes. Okay. So the evaluation tree evaluation based on your tree structure and your tree organization, and then from bottom build up your value. Okay. So one more thing. This tree evaluation, if you have a program structure that is if a greater than 3, and then you do return 1. So this one you pass into a tree, you should have a greater than 3, and then this one is condition. Okay, and condition is under your if. Under your if, you should have a cobra. Okay, and under your cobra, you have the return. And so your passing tree may be like this. So when you evaluate your left-hand side to get let's assume you say you get a true. And then you will evaluate your left-hand side. And then the return 3 will be evaluated. So even it is not an algebraic tree. If it is your syntax tree, your syntax tree will also be evaluated. Okay, but the evaluation function will be different. Okay, so next one is when you evaluate your tree or build your tree, you need to do tree traversal. So your tree traversal is to do top-down traversal over your tree. So basically, usually it is depth first searching and also breadth first searching for the tree traversal. Okay, but sometimes the traversal is based on your evaluation method, not based on your tree structure. Okay, so here this one is tree to be and then there's a post-order, pre-order evaluation. Then you will get 1, 3, 7, 5, and then 8, 2, 9. Okay. Pre-order expression. And you also had an in-order traversal. Okay. In-order traversal, you evaluate your left side first. So you get 7, 3, 5, and then 1, and then 2, and then 8, and then 9. Okay, it's in order traversal. And there's also post-order traversal. Okay, so they are different searching, and when you visit a different node, they are also pre-order and also in order and post-order traversal. So there are several different ways to do traversal. Okay, let's look at this different program. Listing file. So it's right here. We do have listing program. Okay, pre-order, traversal. You have to use the binary tree you define in your path builder. Okay. So right here, this one is a listing file. You had a binary tree. You had a build path tree. And then you had an operator. And then you had 2 integer, 2 string. And there is your evaluation function. And your main program, you build parsing tree, evaluate, and then print out the review. Okay, this one is your listing file. So let's run it. Okay, you got 45. And 45 is the result. So this one, actually, the so-called listing file is from your this course. And let's go to the tree structure. So here you do have the path tree. So today we go through this different chapter for path tree. And then tree traversal. Okay, and in the tree traversal, we have listing 2, listing 3, listing 4, and listing 5. So listing 5 is the one that we used to build the whole thing, including the binary tree and also operator and also the evaluation of the tree. Okay. Okay, anyway, here is the tree listing of the program. Okay, so this one is the listing of the program. Okay, so this one, let me also post it to you to save your time for listing file. Let's look at the listing file B. The listing file B, I think it's also the same program, okay? It's the same program. Why we have listing file B, I forget, okay? It's okay. Okay, So we go through this basic trees theory, and then basically in this basic tree theory, we build our algebraic expression into a tree, and the tree structure is apparently very easy based on your program structure. So earlier we used a step to do evaluation of the expression. At that time, we do not build a tree. So this time we build a tree and we do similar thing, but the purpose is the same. Which one more efficient? Usually is the one that without a tree is more efficient because you kind of do not need to build the tree memory. Okay, but if your tree need to be evaluated for many times, say you have a program that you need to compile it and run the program several times, then the past tree will make sense. Okay, so to build a tree for it or not, that actually depending on your program purpose. Okay, depending on your program purpose. So that's basic trees theory so far. Okay. Now before we actually go to the next part, today we will continue to look into okay, let me create this one. Okay, let's change back to this basic trees theory. We do create a structure for the left right node, okay? And then you can build a class to build a binary tree based on the code that we give you, okay? Based on code here. So we don't repeat those detailed tree building structures. And then next one is that we would like to talk about the Fibonacci sequence one more time. So this is Fibonacci sequence. Actually, we talk about it in the AP concept A. And we do know that f of 5, you need to call f of 4 and call in f of 3. And in f of 3, call in f of 2 and f of 1. Okay. So this one can be your recursive call structure. You do recursive call like this. Okay. You can build a data structure like this to store your Fibonacci tree. So you can basically do the evaluation, but both ways are not efficient, okay? That's the purpose that I'm going to talk about here, right here, okay? So this one, we would say it is not efficient. So I'm going to talk about this Fibonacci tree and multiple way of evaluating it. So let's actually compare and look into the tree structure as well. Okay. Okay, so the first one is the one that we commonly see that actually is okay. We do have a recursive call for Fibonacci. Okay, so this one is a very easy definition for Fibonacci function, but we do know this one is very inefficient in terms of programming. It will be an exponential algorithm. Okay. And right here, we are not arguing about the time. So this one, you will do recursive call, and then the calling structure is a tree structure. Okay, and we are not trying to demonstrate this, but we will actually look into this problem. So this one is the first one if we have the recursive call function. Okay. Second one, if this program we would like to change it to tail recursive. Okay, let's write a tail recursive version of this. So we do have the people, then we will do people helper of something. Okay, we're going to use a people helper of something to run it. Then let's write a people helper. So we would like to have a tail recursive function. So we do have integer n, okay, and we do have f n minus 1, so let's call n1 and f n2, okay. So if n equals 0, okay, you will actually return 0. If n equals 1, you will return 1, okay, and then let's see. No. Right here, let's actually do this. Let's have the integer I, okay. So if n equals I, you will return your fn1 plus fn2, okay, your fn minus 1 and fn minus 2. Okay, otherwise, you will return people helper of n and then I plus 1. So I keep adding. Okay. And then your new fn1 equals this, your new fn2 equals this. Okay. And then right here, when you get started, you do n, and then you starting from 0, and then starting from 2, and your fn1 is 1, so you put 1, and then your fn0 is 0, so you put this. Okay. So this n if n equals 0, you return 0. If n equals 1, you return 1. So this one will perform in the same way as your program. Okay, let's do it this way. Let's do integer I equals 0, I less than equal 40, I increase. Okay. Okay. So something like this. So you do your people 0 to people 40. Okay, so you get all the data like this. Let's actually copy this for loop back to your recursive function. Okay. And let's run this one as well. You will get the same result, but it's actually much slower. Okay. Okay, so compare these two algorithms. What is the main difference? Why this one with a people helper will be much faster? This one for Sherry. Can you answer it?
What about what about this like
Hmm? What?
you meant like how this helps work?
What is the difference between this call? Both are recursive function.
Yeah.
But what is the people helper version is faster?
Sorry, it's what? Sorry, I can hear.
It's
Like,
faster.
faster. Oh.
You compare the code, okay? Let me actually send out both code for you. The reason why I'm talking about this is because when you evaluate a tree algorithm, a different algorithm, you have to think about the implementation issue. Even though both are recursive function, but their efficiency maybe is different. And both are tree structured. When you have the recursive code, both are tree structures. And how comes this one is much faster compared to the one with a helper and the one without helper? This with a helper would be much faster.
Is it because like the helper function does the like the more complicated part quicker?
But why? More complicated structure, why it actually would be faster? Okay, this one for Helen.
Is it because like the Fibonacci with the helper function, once it gets to like the smallest case, it just returns. But for the other one, when it gets to the smaller case, the information has to go back up the line to like do more to it.
Yeah, but that's called tail recursive, right? So tail recursive is more efficient because of the compiler. Yes, because the compiler can optimize the code. So one advantage that is the people helper get it from the compiler. But in fact, this one is more than that, not just the tail recursive part. It is a tail recursive function, so you get some advantage. Other than that, you also have other advantage. So basically in competition, you really don't write the one that doing recursive. You are writing this one. This one maybe, if you do recursive, you may write this version. This one is okay. This one actually is the order n algorithm. The other one actually is the order 2 to the power is power n algorithm. So why this one is only a 2 to the power, this one is the order n algorithm. It is a recursive. This one for Sarah. Sarah, can you answer it?
Sorry, can you repeat the question?
question is why this people helper is more efficient compared with the one with recursive call. This one is the one with a typical Fibonacci function we talk about. This one is a tail recursive people helper. But the answer is that both Helen and Sherry already tell us that it may be because of tail recursion, so a compiler can optimize. So that's actually true, but that's not the main reason. So what is the main reason that is a people helper version will be faster?
Maybe because it's using a helper function. I'm not sure.
But it is using a helper function, but why you write more code, but it actually is more efficient? And there is no tree being built. Okay, there is no tree being built. Both not building any tree. Okay, the answer is the original version. You have F5 calling F4, calling F3, F3 calling F2, calling F1, F4 calling F3, calling F2. So you continue. It is a 2 to the power n algorithm. If you go the original recursive, okay? Tail recursion, you do not need to have extra plus sign. That's true. That's one advantage. And then you can do call, return right away. So actually, compiler can optimize it. That's one reason, but that's not the main reason. The main reason right here is that we use a two index, n and I. So this one is not top down. Instead, this one is the bottom up. So last week, we talked about dynamic programming. Dynamic programming, there are two approaches. Top-down call memorization. Bottom-up call what? Anybody remember bottom-up call what? Bottom-up call tabulation. Okay, this you need to remember, okay? So what is the tabulation you build up? It actually is you will Fn1, you will Fn2, okay? 1 and 0 already been done here. Fn2 will call Fn3, will call Fn4, will call blah, 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 until Fn. So totally the call has n call. It's an order of n recursive call. It's not order of 2 to the power n call. So basically the computing structure is just 1, calling 2, calling 3, calling 4, calling 5, calling up to n. So this recursive structure is very efficient in terms of doing the recursive call for people. So if you can find this structure, you can call this one a dynamic programming. And this dynamic programming is based on tabulation. Let's go back to the dynamic programming one more time. Last week, when we talk about dynamic programming, peak, okay, we actually refer to this website, okay? So remember that last week we go to the coin example, and then right here you do have a Fibonacci function, and then it's saying that there is a tabulation versus memorization, and the memorization is top-down approach. So the coin problem, that you have several different kind of coin. You try to have the minimum number of the coin to get the value. That's called top-down approach because you actually have you have the coin of 26 that will break down into 1 plus coin of, if you use a quarter, coin of 1 plus coin of, if you use a dime, it will be 1 plus coin of 16, something like that. Okay, several cases. So that's actually called top-down approach. And today's approach, we call it bottom-up approach. So this bottom-up approach, actually you build the data one by one from the bottom. Okay, go back to this tail recursive function. It is bottom-up because your I starting from 2. 0 and 1, you don't need to go recursive call, it's actually wasting time, just return it. Then from 2, you actually have your f1 equals 1, f0 equals 0, and your f2 will, if it's equal 2 equals n, then you return this. Otherwise, you return your new f1 and new f2. Does that make sense? Hello?
Yeah.
So what I want to say is that if you know that your call, your program is actually a recursive call, and you may waste your time to do the recursive call in the exponential time, then that's not something you should use it in your what? In your competition, say user code, don't use it, or leak code, don't use it. That will not be the answer. Instead, you will think about, can you find a way to do this kind of top-down computation or bottom-up computation with memory? Does that make sense?
Yeah.
So if this one is a bottom-up, can I work on a bottom-up way to do recursive and using the so-called dynamic programming? The answer is also yes. But the program structure would be more complicated. Okay. So right here, okay, I'm just giving you the example. So telling you that when you go to the user code, what you want to do is right here. You know it's recursive, but you need to figure out, can I do the recursive with dynamic programming so I can save my time so that the bigger case can still be solved? So this problem, okay, let me actually copy this one to another program that's called Fibonacci. But let's don't call it recursive. Let's call it iterative. This one actually in the AP course, I already teach you, but that's actually just compare, okay? Just compare. So this one, we kind of delete it, okay? So these two will return it. And then we are going to do while loop. So integer I equals, let's see. We will integer f1 equals 1. Integer f2 equals 0. Integer f4 is okay, 0. At the end, you will return f, okay? Then you should have an integer I equals starting from 2, okay? And while n, actually I less than equals n. And then your I will increase every time, okay? And here you would have your f equals your f1 plus f2, okay? And your f1 will be equal your f2 would be equal, I'm sorry, your f1 need to be updated first, f2 need to be updated first. Okay. Okay, this would do. Okay, this one would do. This one's is actually the iterative version of the Fibonacci. So this one also we show you in the AP course already. It is order of an algorithm, but this is not what we want to demonstrate right here. Let's try another version. This one called Fibonacci array. Okay, so can we create an array that can solve the problem? Can we? Without doing recursive, let's delete it. Okay. So right here, let's see, you will create integer. Let's do Fibonacci, so let's use this. And this one called n plus 1, okay. And then your Fibonacci 0 should be 0. Your Fibonacci 1 should be equals 1, okay, for integer I. Let's see, okay, right here. Let's actually start right here, okay. So your n may be 0, may be 1. So that's if n equals 0, you still return 0. If n equals 1, you still return 1. Because these two numbers, you directly return a number, you actually don't compute. Then next one, you do I equals 2, I less than equals n, I increase. Your f of I equal to f of I minus 1 plus f I minus 2. And then you return your f of the n. So no while loop. Actually, it's a for loop. It is a for loop. And then you build your data. You have 0 and 1. Somebody's 2, you put in 2. Somebody's 2. I'm sorry, this is 1. Somebody's 2, you put in here. Somebody's 2, you put in here. Somebody's 2, you put in here. So I use an array to solve the problem. And then what is the order? This one is still order of n. So you see, right here, iterative, I have iterative version using while loop without array. I have a array version, also iterative. That's wrong it. You get the same result, right? You get the same result. And then do I need to do recursive? No. Do I need to do what's that? Do I need to do a while loop and then pick up the variable? No, I just use the array and that's solve the problem. Everyone hear me?
Yeah.
So what is the moral of the story? Okay, when we talk about some story, we actually would like to talk about moral of the story. What really we learn from this Fibonacci example? Which one is the most convenient and easier way to do programming? I would say this array version, right?
Yep.
Array version even easier than the while loop. While loop easier than the recursive call. Recursive call easier than the tail recursive version. Tail recursive is good, but tail recursive is a little bit too complicated. But what is the moral of the story? Helen, can you comment on it?
That like a for loop and an array are like the easiest thing to do.
I know,
For most of them.
but here it's because it's a Fibonacci function, so we use array. But
Right.
if
Oh.
if it is not a Fibonacci function, what is the moral story that you will learn from this example?
Like if you're building off of past answers, then you should use an array.
No, actually, the moral of the story is that if you properly select the right data structure, then the algorithm will be greatly reduced for the complexity. That's what I want to say.
Oh,
Hear me?
yes.
If you properly, this one, with the help of an array, compare you have the while loop, you don't have an array. So you need to use backup to compute it. This tail recursion, you need to build the previous curve from bottom and then forward to the next call, forward to the next call, forward to the next call. And then this one, because of no memory, so you actually go deeper to do re-evaluation. So this one, you don't learn anything from re-evaluation. Every time you have a new function, you have to go down to the evaluation tree one more time. So this one wastes the most time. This one, you pick up the data, but it pass over from function. So it actually saves some time, but the program structure a little bit difficult because you need to pass it to the right location. This one, you pick up and using part a little bit easier, but you still need to think about the right structure. Under the array version, nice and easy. You go through your array and then doing one by one visiting, and then you get your Fibonacci number. But this is the moral story. If you pick the data structure correctly, no matter it's tree or not tree, that's another key point. Key point is that can your problem be solved by the easier data structure? And with that easier data structure, you use a very easy algorithm that can solve it. That's the moral of the story. But usually the textbook don't tell you this, okay? Textbook, you can see that AP textbook or any textbook, they don't tell you that a Fibonacci function can be solved by an array. Anybody teach you this? I don't think so. Everyone is talking about a recursive call. But that's not the right way to teach algorithm. The right way to teach algorithm is that you compare different algorithm and then you pick the one that's more efficient and easier to remember. Okay?
Yeah.
Sarah, hear me?
Yeah.
And that's the key idea when you go to user. You need to pick the data structure and algorithm when you see the problem. You have to think about, do I have the order n program to solve it or not? If no order n solution, you have to think about, do I have an n log n algorithm to solve it or not? If no n log n, then pretty much your user problem is wrong. You don't pass your case 10, case 12, right? Am I correct? Usually you
Yeah.
know it's wrong.
Yeah.
So in order to go past the goal division, you have to know about how to pick the right data structure and the right algorithm. As for which algorithm, every problem is different. So I cannot teach you which way you should do. I can only teach you the principle, the rule, how I pick the right data structure. So this one is only an example to tell you a proper data structure can help you reduce the time. But each problem you have to practice to know how you can do it. So the better way still, if you really want to do competition in gold division, from silver to gold, gold to platinum, you have to go through 1,000 of problems. That's the only way you learn different way to simplify the algorithm. Does that make sense?
Yeah.
Okay, and here what I teach you is basic data structure and algorithm. So my job is to introduce you all kind of data structure and all kind of algorithm, and also teach you what is tokenization and what is parsing tree, what is evaluation tree, what is a hash table. Teach you all kind of a purpose of using data structure and algorithm, but that may not teach you which one is the most efficient data structure you should use in the league code or in the user code competition. In the real competition, you still need to figure it out by yourself. Does that make sense?
Yeah.
Unless like you check GPT. If you don't check GPT, basically, you have to come out with the efficient answer by yourself. Here, I just tell you, nobody tell you Fibonacci had this array solution. Before today, I even never teach this one for a student. And I do teach a lot of AP course for the recursive code for Fibonacci. That's just because I want to teach recursion. Okay? But if I need to write a program to give you the best Fibonacci function, I will use this. There are a lot of sequence, a lot of recursive code can be reduced to this format. You have to figure it out. That's called dynamic programming. Dynamic programming is a paradigm. The way you do programming, you either bottom up or top down, and then with some storage. You do recursive code, that's one way. You do for loop, you do while loop, that's another way. So the best thing is that if you can find a while loop and for loop solution, do it. Don't do recursion. If you cannot, you go recursion. And then in the recursion, if you can pass down memory, you pass down the memory. So you can save your algorithm time. Okay, that's the whole thing I try to say today. Okay, so today we finish the basic tree structure. And we also give you this Fibonacci example just to tell you how to select data structure and how to efficiently write your competition programs. Okay? Any question?
No.
No, see you next time. So next time we'll introduce more tree, okay?
Okay.
See
Bye.
you next time. Bye-bye.
再见。